In this video, we are going to find prime numbers p, q, and r such that p cubed equals p squared plus q squared plus r squared. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. We can first try some small values and see how this equation behaves. For example, for the smallest prime, say if p equals 2, then for the other values, q squared and r squared, the sum have to be equal to 4. But apparently there will be no solution, because q and r have to be a prime. We can try one more. If p equals 3, then q squared plus r squared equals 27 minus 9, and that's 18. So by trying, we know that q and r can only be both equal to 3. After that, we can notice one important thing about squares of primes. Firstly, as a perfect square itself, it can only be either 0 or 1 mod 3. But after trying the value 3, if we go for other possible values, then in fact p squared, q squared, and r squared can only take 1 mod 3 if they are not equal to, the base itself is not equal to 3. So that means unless the prime itself equals to 3, or else the prime squared must be congruent to 1 mod 3. Now, if all 3 primes are congruent to 1 mod 3, which means I'm assuming that all 3 of them are not equal to 3, then the sum is equal to p cubed, which is given, have to be congruent to 0 mod 3 because we have 3 ones added together. But this means p must be equal to 3. So it overlaps with the case above, so we can ignore this. Now, ignoring this means we have to go for the opposite, which is either one of q and r equal to 3. Well, if both of the primes are equal to 3, let's see. Then that means p cubed equals p squared plus 18 with a cubic to solve. And factorizing, we will have something like this. Sorry, it should be plus 2p, but it's the same because for this part, there's no real solution. So p can only be equal to 3. But again, it overlaps with our previous cases. So we can just go back to either one of q and r equal to 3, and by symmetry, we can just assume that q equals 3. So therefore, p cubed equals p squared plus 9 plus r squared. Or we can write like this. Next, I'm going to consider mod 4, because when taking mod 4, squares behave in a similar way. They are also either congruent to 0 or 1 mod 4. Unless we have r equal to 2, or else this squared would also be congruent to 1 mod 4. But if r equals to 2, then p cubed minus p squared equals 13. Clearly no solution. So we can just ignore that and say r is congruent to 1 mod 4. And same for p, because we have already tried previously that p cannot be equal to 2. So therefore, p cubed minus 1 is congruent to 1 plus 1 mod 4. So p cubed is congruent to 3 mod 4. And from this we know p can only be congruent to 3 mod 4. Now, you notice that for this prime p is also a divisor of the right side, 9 plus r squared. Because for the left, we can factorize that as p squared times p minus 1. Now, this means r squared is congruent to minus 9 mod p. And I'm going to bring both sides to the p minus 1 over 2 power. Like this, which means r to the power p minus 1 is congruent to minus 9 all to the power p minus 1 over 2. Or I can say that as, for the right side is minus 1 all to the power p minus 1 over 2, splitting the minus 9 into minus 1 times 9. And for the 9, I'll rewrite that as 3 squared. So 3 times 3 to the power p minus 1 mod p. Now at this point, if, well actually we assume that p is not equal to 3, and if it's also not equal to r, then by the Fermat's-Little theorem, then these two terms ought to be congruent to 1 mod p, both congruent to 1 mod p, by the Fermat's-Little theorem. However, for the term that's not highlighted, the index p minus 1 all divided by 2 is odd. And so minus 1 to an odd power is also minus 1. So we are actually having 1 congruent to minus 1 mod p. But that's not going to happen, of course. So that means we've made the wrong assumption. So either we have r equal to 3 or p equal to 3. But for the p equals 3 case, this from our result above, that implies p, q, and r are all equal to 3. But for r equals 3, then we'll have p cubed minus p squared equals 18, and we get similar results. So that means this is the only solution and our final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.